Factors affecting rate of reductive elimination. Factors affecting rate of reductive elimination. First factor, electron density on metal. Okay, electron density on metal. You know, reductive elimination is just opposite as that of oxidative addition. In oxidative addition, higher the electron density on the metal, higher is the rate of oxidative addition. But here, rate of reductive elimination depends on the electron density of metal. When electron density on metal, decreases, rate of reductive elimination increases. That is the point. It is just opposite as that of oxidative addition. When the electron density on the metal decreases, rate of reductive elimination increases. So if the metal is metal having less pi electron density, higher the rate of reductive elimination. For example, write a question. You have to compare the rate PT CH3, here PPH3 triphenyl phosphine, PPH3 triphenyl phosphine, heating in the presence of a DMSO type solvent. Okay, then PT, here CH3, here also CH3, then here PF3, here also PF3. Okay, PPH3 is replaced by PF3, heating in the presence of a DMSO type solvent. You know the product, this CH3 and CH3 is eliminated, here also CH3 and CH3 is eliminated, so your product will be, here the product will be ethane, here also your product will be ethane, CH3. But our question, suppose in the first case the rate is R1 and in the second case rate is R2. Okay, so rate R1 or R2, which is higher? That is our question. So in both these cases the products are same, condition is same, then eliminating group is same. Here metal PT is same, here PPH3, PF3. So your auxiliary ligand or the side ligand or the spectator ligand, that is different. You know, comparing triphenyl phosphine and trifluorophosphine, PPH3 and PF3 having some withdrawing character. Compare, all phosphine ligands are having withdrawing character, but poor withdrawing effect compared to carbon monoxide and nitrosyl. Carbon monoxide and nitrosyl are powerful acceptor ligands. PF3 is also acceptor, but PF3 is sigma star acceptor, so it is a poor acceptor. Okay, so please listen. In this case, PPH3, PF3, comparatively PPH3 is a better donor. Suppose this is electron density 1, this is electron density 2, so PF3 is comparatively better donor or poor acceptor. So electron density 1 greater than electron density 2. Electron density increases, rate decreases because both are inversely proportional. So rate of reductive elimination 2 greater than 1. Rate of reductive elimination 2 greater than 1. So that is the case. Okay, then second factor, metal based factor. factor. When metal size increases, steric crowding decreases, rate of reductive elimination decreases. When the size of the metal increases, steric crowding decreases. Why? For example, nickel, palladium, platinum. Both are same group members. Nickel, palladium, platinum. Suppose you know down the group, size of the metal increases. Nickel is surrounded by 4 ligands. You know the size of the nickel is very small. So a small surface area is available. In that surface area, 4 ligands are coordinated. So definitely steric crowding will be there. But comparatively nickel, palladium, platinum, in the case of platinum having large size, so large surface area is available. So large surface area, 4 ligands are coordinated. In that case, definitely steric crowding will be less. So when size of the metal increases, ligands are attached far away, so steric crowding decreases. And normally, higher the steric crowding, higher is the rate of reductive elimination. So when steric crowding decreases, rate of reductive elimination also decreases. For example, you have to compare the rate. Please listen. First one, nickel, a square planar complex. Here methyl group, here PPH3, here also PPH3. Okay. Heating in the presence of a DMSO type solvent, and this is rate R1. Then second case, instead of nickel, you have to use palladium having large size, a square planar complex. Here methyl, triphenyl phosphine, PPH3, triphenyl phosphine, heating in the presence of a DMSO type solvent, and here rate R2. Clear? So what is the reaction? Reaction same. Methyl and methyl eliminated, ethane will be your product. Then my question, in which case the rate will be higher? What's the point of comparison? Methyl, PPH3, only metal is different. So this is a metal based factor. Here nickel, here palladium having large size, so ligands are far apart. Steric crowding decreases, rate of reductive elimination decreases. So what is the order of rate? Large size, less steric crowding, rate of reductive elimination decreases. So 1 greater than 2. Rate of reductive elimination of 1 greater than 2. So that will be your answer. If platinum is also there, then 1 greater than 2 greater than 3 also. Okay, so this type of questions are also very important. Third factor, cone angle. Absolute name, Tolman cone angle. Tolman's cone angle. Okay, Tolman, T-O-L-L-M-A-N-N, Tolman cone angle. So this cone angle is defined in the case of phosphine ligands. Tolman cone angle defined in the case of phosphine ligands, generally phosphorus. You know, many phosphorus based ligands are there in organometallic chemistry. Okay, so defined in the case of phosphine ligand. Rate of reductive elimination is directly proportional to cone angle. Rate of reductive elimination directly proportional to cone angle. So what is cone angle? Higher the steric crowding, of phosphine ligands, higher the steric crowding of phosphine ligands, higher is the cone angle. Okay, higher the steric crowding of phosphine ligands, higher is the cone angle. What does it mean? What do you mean by the term cone angle? Cone angle is a term defined in the case of phosphine ligands, generally phosphine ligands. Okay, your rate of reductive elimination is directly proportional to cone angle. Higher the cone angle, higher is the rate of reductive elimination. And this cone angle increases when the steric crowding of the phosphine ligands increases. Cone angle means, suppose this is a metal. This metal is connected to a phosphine ligand. You know, phosphine ligand having 3 valency. These are the 3 valencies of phosphine ligand. Is it? The 3 valencies of phosphine ligand can be represented like this. The 3 valencies of phosphine ligands can be represented like this. Okay. So these 3 valencies will create a cone. With the metal. These 3 valencies will create a cone with the metal. At the bottom portion of the cone, there is metal, and these are the 3 valencies of the phosphine ligands. Okay, then my question: if these substituents are bulky substituents, if the substituents, this is the one substituent, second one, third one. If the substituents are bulky substituents, definitely this cone angle theta will also increase. Okay. So higher the steric crowding of the phosphine ligands. Here, suppose here hydrogen. That is called the pH3. Hydrogen having least steric crowding. So then this cone will be a small cone and this angle theta will be very small. Suppose in this case, suppose tertiary butyl. 3 tertiary butyl, very bulky, large cone means this angle theta will also be very higher. So generally this cone angle is defined in the case of a phosphine ligand. If phosphorus containing 3 substituents, R1, R2, R3, phosphorus containing 3 substituents. If the substituents are very bulky substituent, definitely large steric crowding will be there. The cone will be a large cone and the theta will be very higher. So theta higher means rate of reductive elimination directly proportional to the cone angle. Rate of reductive elimination directly proportional to cone angle, and this is called as theta. Okay, so you have to just familiarize the theta value of some popular phosphine ligands. The theta values are given in B.D. Gupta. You have to just familiarize the theta value. Then only in a question you can compare which one having highest steric crowding. Higher the steric crowding, higher is the cone angle. So that data is given in B.D. Gupta. So you have to compare that. Please listen. Please copy the cone angles of some selected phosphines. Cone angles of selected phosphine ligands. Cone angles of selected phosphine. No need to memorize the exact value of cone angle. You have to compare the cone angle. pH3. Phosphorus with 3 hydrogen, least cone angle only 87 degree. Then hydrogen replaced by the small fluorine, PF3 104 degree. Okay. Then POME thrice, comparatively larger, POME thrice 107 degree. 107 degree. Then PME3 with the 3 methyl group, comparatively larger, 118 degree. PCl3 124 degree. Then POPH thrice 128 degree. This is the order, increasing order. Then PBr3 131 degree. That is the Tolman cone angle. Okay. then PET3 and PR3. PET3 means ethyl group, PR means propyl group, both having 132 degree, comparatively same. Then PCF3 thrice, cone angle 137 degree. Okay. PET PH2 140 degree. PPH3 145 degree. Isopropyl PIPR thrice 160 degree. Tertiary butyl tertiary butyl thrice 182 degree. Okay, so these are some popular cone angles which is given in organometallic chemistry, BD Gupta. Okay, now you can compare the steric crowding offered by the selected phosphine ligands. Okay, once again explaining the cone. This is metal connected to phosphorus. You know phosphorus having 3 valency. These 3 valencies will make a cone with the metal. Okay, 3 substituents R1, R2, R3. Okay, this angle is called cone angle theta. Okay, if these substituents are large substituents, your cone will be large cone and angle theta increases. If 3 substituents are hydrogen, PH3 having the least steric crowding, so rate of reductive elimination least. Okay, PH3, PF3, you have to study this order, not this angle. In your exam does not ask what is the cone angle of P tertiary butyl thrice. That type of question is not expected. So PH3 87, then PF3, POME thrice, PME3, PCl3, POPH thrice, BR3, PET3, 3 ethyl, or next PR3, propyl, PR is propyl, then PCF3, PET PH2, PET2 PH, then PPH3, isopropyl. Tertiary butyl is the bulkiest, 182 degree cone angle, very high rate of reductive elimination. I think you got the concept. Tolman cone angle. If you understand this concept, please write a question and compare the rate. Okay, first question. CH3, sorry, not P, it's platinum. Platinum, CH3, this is a phosphine ligand, PME3. Here PME3, heating in the presence of a DMSO type solvent, you will get the product. Then second question, PT square planar complex, CH3, PET3, ethyl, PET3, heating in the presence of a DMSO type solvent. Third one, PT square planar complex, CH3, PTBU tertiary butyl thrice, heating in the presence of a DMSO type solvent. Okay, compare the rate. You have to compare the rate. In all these cases, product will be ethane. You have to compare the rate. You know, these are the auxiliary ligands or spectator ligands. When the steric crowding of these ligands increases, definitely the rate of reductive elimination of ethane will be very faster. Okay, so this is PME3 ligand, Metal is connected to PME3. Here a cone is created. Cone. Metal is connected to PET3. Metal is connected to P tertiary butyl thrice. My question, in which case this cone angle will be very higher steric crowding? PME3, ET3, tertiary butyl. Tertiary butyl is very bulky, large cone angle, large steric crowding, elimination very easy. Then PET3, then PME3. So rate of reductive elimination of 3 greater than 2 greater than 1. Clear? Due to P tertiary butyl having large cone angle, theta, large cone angle. So that will be your answer. Fourth one, bite angle. Not cone angle, this is bite angle. Bite angle. Okay. Cone angle and bite angle are different concepts. Rate of reductive elimination proportional to bite angle. Rate of reductive elimination proportional to bite angle. For example, write a question. W tungsten methyl group here a CP ligand, here another CP ligand. Okay, heating in the presence of a DMSO type solvent. This is the first question. Second one, tungsten, here a methyl group, CP, here also another CP. Okay, these two CPs are connected by a CH2 bridge. So these two CPs are connected. So bite angle theta, you know, cone angle is defined in the case of phosphine ligands. This bite angle is a ligand. This angle is called bite angle theta. This will be the metal ligand. Okay, here an angle theta is there. You know the product methane and methane are anionic ligand, they will be eliminated as ethane. Here also methane and methane are anionic ligand, they will be eliminated as ethane. Okay, then here please listen. Metal ligand, this angle is called theta. This is theta 1, this is theta 2. So cone angle is between metal and the same ligand. Metal and the same phosphorus ligand, that is cone angle. Here bite angle is 2 ligand and metal. That angle is bite angle. So rate of reductive elimination is directly proportional to bite angle. Okay. So my question, in which case this bite angle will be larger? Larger the bite angle, larger is the reductive elimination. Rate of reductive elimination. So here theta 1, here theta 2. Here two CP rings are attached or they are joined by a CH2 bridge. Okay, here these two CP rings are more, they are not close to each other, but these two CP rings are close to each other because both of them are connected by a CH2 bridge. So definitely this angle will be large angle compared to this one. So you can say that theta 1 greater than theta 2. Why theta 1 greater than theta 2? Theta 1, here two CP rings are largely separated, but here they are joined by a CH2 bridge. So definitely theta 1 greater than theta 2. Okay, theta 1 greater than theta 2. So what will be the rate of reductive elimination? Rate of reductive elimination 1 greater than 2. Higher the bite angle, higher is the rate of reductive elimination. Okay. Then write one of the previous question in NET exam. Another previous question, very important question. First question, a platinum based compound Me PPH2 PPH2. Okay, here an angle theta is there. This is not the cone angle, a phosphine ligand, but ligand metal ligand angle. But in cone angle, metal ligand, that angle is in the same case. Okay, so this is bite angle theta, not a cone angle. Both are different, entirely different concept. Okay, second question, PT, very important, methyl hydrogen, PPH2, okay, here a ferrocene, you know about ferrocene. About the ferrocene, here PPH2, PPH, sorry, this is connected to PPH2. Okay, both of them heating in the presence of DMSO type solvent. Here also the cone angle is there, metal, ligand metal. This is theta 2, this is theta 1. My question, which one having the highest rate of reductive elimination? You have to consider the bite angle. Okay, so in both the case, methyl. A methyl is eliminating. Okay, methyl eliminating group is same, conditions are same. Okay, then here also PPH2, but this PPH2, here also two PPH2 ligands are there, PPH2 angle theta. Here also PPH2 angle theta. Then my question, theta 1 or theta 2, which one will be larger? That is my question. Once again repeating, platinum is connected to PPH2. Platinum is connected to PPH2. But here how many atom separation is there? These two PPH2 are separated by 2 atoms. Okay, these two PPH2 are separated by 2 atoms. A 2 atom separation is there, a 2 carbon separation is there, or 2 atom separation is there. But here these two PPH2 are separated by 1, okay, 2, 3, 4. Number of separation is 1, 2. This is actually coordination. This 2 is not calculated. 1, 2, 3 atom separation is there. When the number of atom separation, here these two PPH2 are separated by only 2 atom. Here a large separation is there. These two PPH2. When number of separating atom increases, when number of separation increases, definitely this angle will also increase. Clear? When number of separations, suppose these two PPH2 are separated by 2 atoms, here 2 PPH2 are separated by 5 atoms, definitely this angle will be larger. So in this case, theta 2 greater than theta 1. So you can say that rate of reductive elimination in 2 greater than 1. Rate of reductive elimination in 2 greater than 1. That's a concept of bite angle. Fifth point, coordination of ligands. Coordination of ligands. Please listen. For comparison, write a question. Nickel, PME3, PME3, one second. Heating in the presence of DMSO. Same question. First step, coordination with an alkene. Coordination with an alkene. Then heating in the presence of DMSO. First step, second step. Okay. So same reactant, two cases. We have to compare the rate. First of all, write the product in both of the cases. First of all, write the product. Heating in the presence of DMSO, PME3 is neutral, PME3 is neutral. These two are anionic ligand. So here bond cleavage takes place. Between these two, a new bond will be formed. So your product will be like this. Right or not? Right or not? To triangle. Here between these two atoms, a new bond is formed. So that will be your product. But here in this case, first step, this alkene, this C double bond of alkene will coordinate to the complex PPH3. Then here your alkene double bond O, double bond O. Okay. First step, that alkene will be coordinated to this, and you know, this alkene is a pi acceptor ligand. This alkene is a pi acceptor ligand. In first case, this is case 1. In case 1, the two anionic ligands are directly eliminated. Reductive elimination. What type of reaction? Reductive elimination. Here first step is not reductive elimination. This is case 2. In case 2, the first step is not a direct reductive elimination. Instead of a pi acceptor ligand is coordinated to the metal. As when a pi acceptor ligand is coordinated to the metal, definitely the metal electron density decreases. When metal electron density decreases, definitely the rate of reductive elimination increases. So it will immediately gives the product. Both of them give the same product, but rate in the second case greater than first case. Why rate in the second case greater than first case? Because in second case, a pi acceptor ligand will coordinate to the metal, that will decreases the electron density on the metal. As a result, the rate of reductive elimination in this case will be faster than that case. Okay, so coordination of a pi acceptor ligand will definitely increases the rate of reductive elimination. And the last factor, sixth factor that affects rate of reductive elimination. We discussed the many factor. Last factor, chelating and non-chelating ligand. Chelating and non-chelating ligands. Okay, chelating and non-chelating ligands. Rate of non-chelating always greater than chelating complex. Rate of non-chelating always greater than chelating complex. For example, here PT platinum with the 6 coordination site. Here a methyl group is there. Here a methyl group. Here PPS2, DPP, diphenyl phosphoethane. Here also PPS2. It's a chelating ligand heating in the presence of a DMSO type solvent. This is the first question. But second question, a platinum complex, octahedral complex. Here methyl. Here these are bident chelating ligand. Its monodentate analog is PPS3, heating in the presence of a DMSO type solvent. My question, in which case the rate of reductive elimination will be faster? In both the case your product is 2 methyl groups are eliminated. Here also 2 methyl groups are eliminated. In which case rate of reductive elimination? That is again always the rate of non-chelating will be greater than chelating, because in the chelating ligand these ligands are connected. As a result, the steric crowding will decrease and rate of reductive elimination will decrease. Okay, so rate of non-chelating greater than chelating complex. So definitely this is the chelating analog, that is the monodentate analog. So definitely rate of 2 greater than 1. So these are the 6 factors affecting the rate of reductive elimination. So next question, when aryl and alkyl anionic ligands are present, when aryl and alkyl anionic ligands are present. Later we discussed when more than one anionic ligands are present, CH, HH, CC, CX, that's the order. When aryl and alkyl anionic ligands are present, for example, write a question. PT, platinum, methyl, here an aryl group, here Me, here iodine, here PME2PH. It's a worked out example. PME2PH, here also PME2PH. Okay, heating in the presence of simply heating. But listen, here this is methyl minus, iodine minus, aryl minus. So platinum plus 4 oxidation state. You know platinum plus 4 oxidation state is a special case. In that case trans elimination takes place. So methyl iodide is eliminated. So but I am using a polar solvent. Heating in the presence of a polar solvent. In the presence of polar solvent, what takes place? Polar solvent, the eliminated I minus is solvated. So SN2 attack does not take place. Usual elimination, cis elimination takes place. In the presence of polar solvent, cis elimination takes place, not trans elimination, usual product. Then here alkyl and aryl groups are there. This is methyl group hybridization sp3. This is methyl group hybridization sp3. This is aryl group hybridization sp2. Okay. Then our question, whether methane and methyl eliminated as ethane, that's the first probability. What are the possible product? These two CH3 can eliminated as Me, that is called ethane, first possible product. Then when aryl and Me can be eliminated as toluene. Toluene is your second possible product. Then my question, which one will be your major product? That is our next rule. Okay, so reductive elimination is a favorite area of any competitive exam. Okay, in organometallic chemistry. Okay, first point, in higher oxidation state, here oxidation state of platinum is 4+. That's a very higher oxidation state. In higher oxidation state, sp3 elimination. sp3 elimination. And in lower oxidation state, sp3 sp2 elimination. That is the hint, not this hint, and give a star mark. Okay. So if your metal is in higher oxidation state, to sp3 elimination is favored. But when metal is in lower oxidation state, sp3 sp2 elimination takes place. Here platinum in higher oxidation state, platinum 4+. So definitely my question, sp3 elimination or sp3 sp2. This is an sp2 carbon. Which one will be your major product? sp3. So this will be your major product. Okay, so in such cases, ethane will be your major product, since you are using polar solvent. Okay, then write the next question. Write the next question. Write the next question. Another type of question. PT, PPH2, diphenyl, PPH2, and these two are connected by a 6-membered ring. Okay, and here an aryl group sp2. Here a substituent R1 is there. Here another aryl group. Here a substituent R2 is there. So heating in the presence of DMSO. Heating in the presence of a DMSO type solvent. Clear? Heating in the presence of DMSO. Here both are sp2. So definitely elimination will be these two rings, because both are sp2 elimination. There is no sp3. Then my question, you have to compare the rate. Rate depends on R1 and R2. Rate depends on these two substituents at the para position. These two substituents at the para position, R1 and R2. If R1 and R2 are electron donating group and electron withdrawing group, then highest rate than electron donating group and electron donating group, or electron withdrawing group and electron withdrawing group. So that will be the last point. Okay, so in this case rate of, if R1 and R2 are, suppose 2 questions are there, 2 aryl system. Here 2 substituents are there. One is electron donating and other is electron withdrawing. In the second question, both are electron donating or both are electron withdrawing. Here comparison is not possible. Okay, then which one having the highest rate of reductive elimination? When one of the R1 is electron donating and other R group is electron withdrawing. So that's the highest, right? So our topic reductive elimination is almost completed. So you have to write some homework questions. Then we can wind up this section. Okay, homework. First question. RH octahedral complex. Okay, NH2, CH3, hydrogen, CO, heating in the presence of a DMSO type solvent. Heating in the presence of a DMSO type solvent. Second one, same rhodium, octahedral complex, hydrogen, CH3, NH2, carbon monoxide replaced by thiocarbonyl. Instead of CO, thiocarbonyl, heating in the presence of DMSO. So compare the rate of reductive elimination. That is the question. Compare the rate of reductive elimination. Very important. Okay, then next question, one more question. This is first one. Second one. Here also same, compare the rate of reductive elimination. PT, CH3, PPH3, heating in the presence of DMSO. Next set of question. First one, second one, PT, CH3, PPH3, second question. Third question. 1 second. Heating in the presence of DMSO. All these are previous year questions in many competitive exam. Okay, so how you can approach these two questions? I will give you a hint, then you can practice. Okay, first of all, in such type of question, you have to identify the point of comparison. Heating in the presence of DMSO, heating in the presence of DMSO. NH2CH3H, NH2CH3H. When more than one anionic ligands are there, which one will be eliminated? You know the order of elimination. CH having the highest order of elimination. So your product will be methane. In both the case. But our point of comparison is the CO and the CS. This is carbon monoxide. This is thiocarbonyl, CS. In the IR stretching frequency of metal carbonyls, I have already given an order. Thiocarbonyl is a powerful electron acceptor than carbon monoxide. The electron withdrawing tendency of CS is comparatively higher than CO. So definitely this is a good acceptor. Electron density decreases. When electron density decreases, you know what happens. Okay, so that is a hint for the first question. Then please listen. Here it's an important question. Please listen. 1 second. Okay, so in all these cases, platinum 2 plus, that will be the oxidation state. Your eliminating group is CH3 and CH3, they are eliminated to form ethane. Okay, here these eliminating groups are cis to each other. When they are cis to each other, rate of elimination will be very faster. Mechanism is concerted mechanism, very fast rate. But here the eliminating groups are trans to each other. So trans elimination is least favorable. So in the trans complex, first of all, this trans will undergo isomerization and it will be converted into cis form. Then only elimination takes place. A square planar trans complex can undergo isomerization reaction. So on heating with the DMSO, first of all, this will be undergo isomerization to form the cis isomer. Then only elimination takes place. So first step is isomerization, then reactive elimination. So comparatively slow process. Process is slow. So highest rate when they are cis to each other, then trans isomer. Here also these two CH3 are trans to each other, but here one important thing, this is a rigid system. You know, this system is a rigid system. Here isomerization not possible. Here isomerization is possible, but here it's a rigid system. It's a part of a ring. It's a part of a cyclic ring. Here isomerization does not take place, so it will always exist in trans form. So this will not show reductive elimination, but this will undergo reductive elimination on heating by isomerization. A square planar trans complex undergo reductive elimination by isomerization reaction, but in a rigid system like this type of rigid system will not undergo reductive elimination. So this is having the least rate and they are trans to each other. Okay, so what is the order of rate of elimination? Cis greater than, trans greater than rigid. Rigid does not undergo reaction, and also that will be, you have to practice the question. So our reductive elimination topic is officially completed.